Good evening. Thank you for having me. I'm sorry that I was not able to make it there physically. Nonetheless, I hope I can share what I had learned through this virtual presentation. So I'm going to talk about two new cases of physics beyond the standard model with a question mark. First, I'm going to talk about the Muon g-2 experiment. So in the Muon g-2 experiment, we're looking at the anomalous magnetic moment. And to understand what the G means, I will explain it in the same way it is often explained in journal articles or other empiriometric discussions. So please bear with me here. So first, to make sense of the G factor, consider an electron going around in a circle like shown in the figure here. So we are essentially talking about this as a classical particle. And if you calculate the magnetic moment of this charge going around in a current carrying loop, let's say, then you can write the magnetic moment as I times A, where A is the area. Here they're bolded because both are we're depicting both as vectors. And then you can see that the magnetic moment coming from this orbital motion of the charge going around is related to the orbital angular momentum given by L, and there is a factor before L that is given by E by 2m. So this is completely a classical picture of the electron going around. Here we did not consider anything about the electron itself having a spin. So now, if you consider just the electron by itself, the electron is not necessarily going around in any orbit. It's just the electron. It has spin, which is often described as some sort of angular momentum in the empiriometric sense. And so by extending this, whatever we have for the orbital angular momentum, that is, if we consider the spin of an electron on par with orbital angular momentum, which we will discuss whether it is apt or not later. But then it is seen that the factor that you get here, E by 2m, is not the same as orbital angular momentum, but it is twice as much. So you actually get, if you substitute instead of this L orbital, if you were to substitute S for standing for the spin of the electron or any lepton, then you would get the charge of that divided by just the mass. So that is what is the what is called the G factor. So the G factor would multiply this entire E by 2m, so that if the G factor is 2, then this 2 and the 2 in the denominator would cancel out. So you would get E by m if you had S instead of L here. So the G factor is what multiplies this E by 2m when instead of orbital angular momentum, we are considering this intrinsic spin of the electron, the magnetic moment associated with the spin of an electron. So experimentally, this can be measured. And the way to measure it is, for example, if you consider an electron, it has spin. So if you put it in a magnetic field and it's going around, then the spin is precessing around the magnetic field. So there are two motions in a way. That is, one is if you consider the spin vector, again, I'm talking about it from sort of a purely mathematical or a geometric rather point of view, where the spin vector is precessing around the magnetic field, and the electron itself is also going around. So by looking at these motions, by looking at the Larmor frequency of the spin, one can determine what the G factor should be. And so that's how we can experimentally know the G factor. And this can be explained sort of from Dirac's relativistic equation for spin half particle. So the the first equation is the relativistic one, and the second one is the non-relativistic Dirac equation. So if you compare the second term in the non-relativistic Dirac equation, you can see that the factor that would come out of the second equation should give you the value of g, and the Dirac in fact calculated it to be 2. G is equal to 2. But experimentally, G for an electron has been observed to be greater than 2, that there is an extra addition to 2. And Schwinger calculated the first extra term. So we can first define the anomalous magnetic moment based on the G factor. So the G factor, as calculated by Dirac, is 2. G is equal to 2. So any deviation from this G is equal to 2 is what we are considering as an anomaly. Rather half of that. So G minus 2 by 2 is what we are defining as anomalous magnetic moment for the electron. So instead of electron, if we have muon, then it would be G mu minus 2 by 2. And Schwinger used Feynman diagrams like you see here, that if you have, let's say, an electron, you see a blob in the center. This blob basically includes interactions with all things like different leptons, different hadrons, different weak interactions. All sorts of things are included in this blob. So this blob can be broken down into different terms. As you can see, you can keep adding as many terms, starting from no virtual particles, as Dirac did, where you get G is equal to 2, to having one virtual particle, to having two virtual particles, so on and so forth. So what Schwinger actually did was he calculated the first Christmas tree here. So that's this one, and for the first Christmas tree, you would get an extra term that is given by the fine structure constant alpha by 2 pi. So in fact, this can also be seen in sort of Lamb shift, right? So just purely from, if you consider only the first one here, then basically you wouldn't have any difference between in a hydrogen atom. If you look at the P and S wavelengths, then you won't have any. They should be the same. You should not see any Lamb shift, but we do see Lamb shift. So this fine structure constant and anomalous magnetic moment are related. So in a way, by measuring this anomalous magnetic moment, we are sort of measuring fine structure constant, and the fine structure constant, as I have mentioned, is also related to the Lamb shift. So now, because this blob has everything, it's a difficult thing to calculate what this anomaly should be from a theoretical standpoint. So we can calculate this anomaly here by considering higher order. So we can consider, this one, or one with 3 virtual particles, or one with 4, and so on and so forth. And then again, this could be, another lepton or a hadron, or different things. So there are a lot of possibilities that are there. So they introduce a lot of error into calculations. But we can sort of look at this anomaly in sort of 3 parts. The first part could be quantum electrodynamics. So you're just thinking about virtual photons. So these strings are just virtual photons. But you could have hadronic or weak, or if there is something beyond this, then you have something BSM that is beyond the standard model. That's the new physics. So the question is, if we calculate all these values very well, and then if we still see an anomaly that cannot be explained by all these QED, hadronic, weak interactions, all these things, then that means there must be some new physics beyond the standard model. What that essentially means to me is that we abstracted too much here in this part, that there's as such, there is a lot of poetry there, and we have not realized, what that poetry exactly is. So in calculating this, the biggest uncertainty comes from hadronic component here, and hadronic component is very difficult to calculate because there is in QCD there is asymptotic freedom, which means for example, if you have quarks going away, then in this asymptotic freedom, it is often described as the strength of interaction is increasing as they're going away. So because of that, this hadronic part is often calculated using dispersion, and there is a lot of uncertainty in there. And so I have taken some of the calculated values from this paper here, and then so you can combine all these three parts, and then you get this. So here Al denotes the lepton. So here we're calculating for a muon, and one might wonder, why did we choose muons instead of electrons or leptons? So if you look at this anomaly in the magnetic moment, it somehow depends upon the magnetic moment of the lepton itself plus the virtual particle mass. So it goes as something like, if m is the little m, tiny m is the magnetic moment of the lepton, and capital M is the magnetic is the mass of the virtual particle going around. That's the virtual particle that we are talking about here. Then the anomaly depends as m, little m by capital M whole square. That is, if you have an electron, the electron is very tiny, so it doesn't, because of its tiny mass and tiny magnetic moment, any heavier particles, any heavier virtual particles here would not really appear as an anomaly. They're very hard to measure. But the magnetic moment of the lepton is several thousand times different than the electron. So the involvement of higher order virtual particles, especially the hadronic part, is more visible in case of muons. So these are even more visible, should be even more visible in case of tau, but that has very less lifetime. So muon then, which is in the sort of in the middle, that is, it shows some change, but it also has microsecond lifetime. So it's sort of something that can be handled and experimented with. So how the theoretical errors from the hadronic part are actually evaluated, I was not able to go much into that. I actually couldn't find more details about it, and it's always buried in a lot of equations, and it's very hard to understand what is physically happening there. But the experiment itself involves now that you take a target. This target could be made of beryllium or just carbon, and you shoot some protons at this, and that produces essentially pions. So you can look at pi plus, and then the pi plus gives you decays. It's unstable, so it decays into mu plus. So mu plus means that mu plus would decay into a positron and then two neutrinos. So any muon decays into either an electron. A negative muon would decay into an electron plus two neutrinos, whereas a positive muon would decay into a positron plus the same charge is conserved there, right? So you have the same charge on the other side. So we're considering mu plus here, so which comes from pi plus, which comes from the carbon target that is exposed to protons, and these can be channelized and injected into an orbit. So you have a magnetic storage ring that is shown here. And so in this magnetic storage ring, these muons are being injected into that. So as the muons are going around, this muon is going to decay. And because of this decay, you're going to get a positron from mu plus. And these positrons would have the highest energy along the direction of the spin of the muon. So then as the muon is going around, you can have calorimeters around in the storage ring, and you can detect the positrons that are coming out. And the maximum energy of this positrons would be coming out along the direction of the spin of the mu plus. So we can see how the spin is precessing. So we can know the precession frequency. And from that Lamarck precision frequency, we can calculate what is the anomaly that should be there in the G factor. So that's how it is done, but the experiment is not as simple as it sounds. It never is. So here it doesn't. You cannot have just only a magnetic ring. You need to actually apply an extra electric field, a stabilizing electric field, a quadrupole field, because as the muon is going around, you want it to be you want the vertical stability. So you apply the extra quadrupole to have, because your calorimeters we're using calorimeters that are positioned at certain places to detect these positrons that are coming out, so we can know the direction of spin of the mu plus. So because these positions of the calorimeters are fixed, we cannot have an orbit. If you have an orbit that is not vertically stable, then basically we cannot make any meaningful sense out of the data that we see. So that's the reason why you have to apply an extra quadrupole field to sort of provide this vertical stability, because we are fixing the calorimeter positions. And so we get, if we didn't have this extra term, the stabilizing field, then we would get only this term, that is, the precision frequency here that you see here. You have the term here and the B field, right? And so knowing the B field, knowing the frequency, you can calculate, knowing the mass of the muon, knowing the charge, we can calculate what A mu is from the experiment. So how do we get rid of this extra term? There is a clever way of experimentation, that is, you choose the energy of the muons in such a way that this term can get cancelled. But that would really mean that you know A mu beforehand to choose that electric field, right? And so if you choose this muon energy with 3-point GeV, and this extra term is also coming because recall that the muon itself is going around in the loop. That's why this extra term is appearing. So if you choose the right muon energy, then these two would have been set to cancel out. I don't know how exactly that is verified, but that's what the papers describe. And then so you can use the calorimeter, so you can see, so the muon itself is going around. So we're looking at a zoomed in version of this magnetic ring, and so you can see the P is the momentum of the muon. So the muon itself is going along this dashed trajectory around in a circle. So as the muon is going, the muon spin is at some direction shown by this green arrow, the muon spin, and so the positrons of maximum energy would be emitted or would be going along that direction. So and that you measure using the calorimeters placed inside. So you get the energy as a function of time. So we can see where the highest energy ones, which direction they're getting going in. So we know the direction of the spin of the muon, and by looking at that precision frequency, you can calculate A mu. So as you can imagine, there is a lot of scope for experimental error in all these things. And of course, this is not going to be done with just one muon. This is going to be done with several muons, and several things are sort of ignored here, swept under the rug here, especially several fundamental questions. And then so we need a certain standard deviation to make sure that whatever difference between the standard model and the experimental value is not coming because of some sort of an experimental error. Or some sort of what is called as a random fluctuation. So the experiments before have observed an anomaly, but it was within 3.6 sigma, the deviation. So you can think of to understand this from an analogical point of view, you can think of two lights, and if they are at a certain distance, then you can say that they're different in that way. So the present experiment gives around 4.2 sigma, but I don't think it yet indicates anything about anything beyond the standard model. So this is how it is typically presented, and the questions, the fundamental questions that come up are, we first should go from what we know to what we don't know. But here, the classical part itself, what is magnetism, is itself not very clearly known, and so we're starting off on shaky ground right there. And so it's even harder to understand what the spin is. It's often pushed off as a mathematical object, with it operating as similar to angular momentum. So a lot is borrowed from angular momentum operations. But in case of an electron, the spin itself, what it means, needs to be understood, because if you consider an electron going around, or a charge going around in a circle, if it's going to be stable, for example, like in an atom, then there must be some interaction with the guide wave, so that this energy is being exchanged between the guide wave and the electron. So that part has to be considered. And the second thing is that here all the leptons are sort of considered as with no internal structure, but a lepton, an electron, is a physical thing, and so it has some parts, so it has some internal structure, and that internal structure is not considered at all. So so it remains to be seen whether the standard model comes because there is whether the deviation is real, first of all, and if the deviation comes because of some existence of new particle, or just because we have ignored the internal structure of the lepton. And I think I'm heavily over time, so I'm going to stop here. I'm sorry I went over time, and I didn't get a chance to explain some more detail, some more thoughts that I have on how to go about correcting this by putting first things first, and from an IAP standpoint. But hopefully we all would meet sometime in the future, and then get to discuss more of this. And thank you for your patience, and thank you for giving me this opportunity.